Hello everyone, welcome to LeetCode Weekly, where every week we cover a few LeetCode problems. This problem comes from LeetCode's bi-weekly contest. Problem 3737. Count subarrays with majority elements. So we're given an array of numbers and we're also given a target value. Our job is to count how many subarrays from this array have the target as the majority element, meaning that the target must appear strictly more than half of the time inside that subarray. To make this easier to think about, there's an interesting trick. Instead of keeping track about how many times the target appears versus how many times it doesn't, we convert the array into a new sequence. Whenever a number equals a target, we write down +1, and whenever a number is not a target, we write down -1. Now something interesting happens. For any subarray, if the sum of these +1s and -1s is positive, this means the target appears more times than all other numbers combined. In other words, the target is the majority element. To check this efficiently, we use prefix sums. A prefix sum at position R tells us the total of all these +1s and -1s from the start of the array up to that point. A subarray from L to R has a positive sum if the prefix sum at R+1 is greater than the prefix sum at L. So for every ending position, we just count how many earlier prefix sums are smaller. Because the array is only up to 1,000 elements long, it's perfectly fine to check all pairs of prefix sums and count how many satisfy this condition. So let's start by storing the length of the input array, so n equals len of nums. Now we'll transform this array into +1 and -1. So we'll create a new variable arr, and we'll use list comprehension. So it'll equal 1, it'll put in 1 if x is equal to target, else -1 for x in nums. Now create a prefix sum array with a size of n+1, starting with all zeros. Now we'll loop over each index of the input array, and we'll build our prefix sums. So here we're saying prefix of r essentially equals prefix of 0 plus array of I, which is array of r-1. Now this will populate our prefix sum, and we'll set our answer to 0 initially, and now we'll count the pairs L is less than R, with prefix sum L being less than prefix sum R. So for R in range 1 and n+1, so this is going through the numbers array, and then for L in range R, if the prefix sum at L is less than the prefix sum at R, we are going to add 1 to the answer. This is checking if the subarray sum is positive, which would mean that there is a majority element there. And once this loop is done, we can simply return our answer. As for complexity, this fits in a time complexity of O of n squared and a space complexity of O of n. And this easily fits within limits since n is less than or equal to 1000. So if we run this and check, and it's been accepted, and if we submit, yeah. Let's consider a more difficult version of the same problem. We still have an array of numbers and a target, and we still want to count all subarrays where the target is the majority elements. The basic trick is the same. Convert the array to +1 for target and -1 for everything else, and the subarray has a target as majority if the sum of this transformed array is positive. But now the array can be very large, up to 100,000 elements. The O of n squared approach from before, checking all subarray start and end pairs, is too slow. So we need a faster method. We calculate prefix sums, then for each position we want to know how many earlier prefix sums are strictly smaller. To do this efficiently, we can use a Fenwick tree, which is a data structure that can count how many values are below a threshold in a log of n time. We can also use coordinate compression, because prefix sums can be negative or very large numbers. This maps all prefix sums to a small range so the Fenwick tree can handle them. Finally, as we iterate through the prefix sums, we count how many previous sums are smaller to add to the total and insert the current sum into the tree. At the end, the total count gives all subarrays where the target is majority. This approach runs in O of n log n, which is fast enough for n up to 100,000. We'll start the same way by defining a variable n, which will be a length of our input array. And we'll transform to the nums array to positive and negative ones. And now we'll compute our prefix sums. So we'll create our initial prefix sum array, which will be full of zeros for n+1 length. And then for I in range of n, we'll populate our prefix array. Now we'll create a coordinate compression of all our prefix sums. So we'll first start off by creating a variable allVals, which will be equal to sorted of set of pre. This will return a unique and sorted prefix sum array. And then we'll create a new variable, rank, which will return a dictionary. V, which will be I+1 for I and V in enumerate all values. This is going to map each prefix sum to a rank, which will be 1 indexed, because of the +1. And now we create our Fenwick tree, which is also called a binary index tree. So bit will equal 0 multiplied by, so with the length of our ranks dictionary plus 2. So we need it to be slightly larger than rank, which is why we add the 2 to it. Now I'll create two helper functions. Def update, which will take in an index input, and while I is less than the length of our binary index tree, we'll add to the index, and then we'll move on to the next index in the tree. And now I'll create another helper function called query, which will not again take in index as input. And we'll create a variable result, which we'll set to 0. And while I is greater than 0, we'll add to our result with the binary index tree at the ith position. And again, we'll move to our parent, which is done like this. And we'll return the results. Now with these two helper functions, we can create our answer variable, and we'll loop through our prefix sum array, and we'll get our compressed rank, and add to the answer by querying our bit with r-1, and then we'll update our binary index tree. And we'll return our final answer. So let's test this out. And it's been accepted. And if we submit. Yeah. Thanks for tuning into LeetCode Weekly. If you enjoyed this video, then be sure to like and drop a comment down below. Thanks for watching.